Digital humanities on the semantic web, from infrastructure to practical applications, data analysis, AI-based knowledge discovery, and the web of wisdom. This keynote overviews our experiences in Finland starting from 2001 on building a national semantic web infrastructure for publishing and using cultural heritage contents on the semantic web for digital humanities research in the era of AI. I am Eero Hyvönen from the Aalto University, University of Helsinki and Geneva Graduate Institute. I will first outline a roadmap from research in artificial intelligence, semantic web and digital humanities to what can be called a web of wisdom. According to our experiences, a national semantic web infrastructure for cultural heritage is needed, extending the generic international semantic web infra. The rest of the talk describes results and lessons learned in Finland on creating such an infrastructure with tools and applications that have had up to millions of end users. The presentation is based on work of tens of researchers of the Semantic Computing Research Group at the Aalto University and University of Helsinki, in collaboration with tens of memory organizations and their experts in memory and other organizations in Finland and beyond. Let us first define the needed components for a web of wisdom, that is, artificial intelligence, semantic web, and digital humanities. Aristotle is considered the father of artificial intelligence, who invented the idea that forms the basis of the field, namely the representation of knowledge as ontologies and the rules of logic for formalizing thought, syllogisms. The invention of artificial intelligence is dated back to Alan Turing's paper published in 1950 and the first artificial intelligence conference held at Dartmouth College in 1956. However, the idea of artificial neural networks, which is the basis of today's large-scale language models, was already born in the previous decade. Two very different branches of artificial intelligence research emerged: classical symbolic artificial intelligence and subsymbolic AI, based on learning neural networks and probability theory. A hot research topic today is how the advantages of these approaches could be combined and challenges such as hallucinations minimized in so-called neurosymbolic AI. AI research was born in the 1950s, but the starting shot for digital humanities was fired as early as 1949, when Jesuit Roberto Busa, in collaboration with IBM, began indexing the writings of Thomas Aquinas for computational analysis. Digital humanities research is located at the intersection of the humanities, social sciences, and computer science. The goal is, on the other hand, to utilize computational methods in research and, on the other hand, to study the digitalization of the world and its phenomena. But which digitalization phenomenon has changed or is changing our society the most? At least that should probably be studied in digital humanities. It has been said that the World Wide Web is perhaps the most transformative digital phenomenon since the invention of the computer. The web was invented in 1989 at CERN, Geneva, by Tim Berners-Lee and his colleagues, and shortly thereafter, in the 90s, he also came up with the idea of an intelligent semantic web. International research in the field accelerated rapidly in 2001 under the leadership of the W3C organization, which coordinates the infrastructure work of the web. One of the turning points in research was the article The Semantic Web by Tim Berners-Lee, James Hendler, and Aalto alumnus Ola Lassila. Semantic web research combines computer science programming, artificial intelligence research, and web technologies, mutually reinforcing each other. What if we combine digital humanities and semantic web research? What added value would that create? I have been grappling with this question for the last 25 years, a quarter of a century. The Semantic Web Journal turned 10 in 2020. I was asked to write a visionary article for the anniversary issue about the development and future in the field. In my article, I took the perspective of the changes in paradigm of publishing cultural information. The development began with the skills of writing when, for example, in China, biographies of the deceased were engraved on tombstones and books were printed even before Gutenberg. With information technology, databases and web services were created in the 90s. We started forcing Sampo systems, applications for digital humanities, in the third phase of change, the data revolution and the emergence of the semantic web. The idea is to publish online materials not only for people to read, but also for computers to interpret as semantic data. This enables intelligent search functions, browsing, and data analysis and visualizations of digital human paths. We are now entering the fourth era of artificial intelligence, where computers are not just passive tools, but also active agents that can independently find interesting phenomena in the data, solve problems, and also justify their answers, that is, answer the question why. Also, the editors of the Journal of Web Semantics invited me to write a visionary article for their special issue on how the semantic web is developing in the future. In my article, I applied the data, information, knowledge, wisdom hierarchy of data science for this. The idea is that new value is added as raw data on the bottom is transformed into information, know what, to knowledge, know how, and finally to wisdom, know why. At the same time, traditional web is transformed on the left into the semantic web on the knowledge layer and finally into something that can be called web of wisdom on the wisdom level. The semantic web is already rooted in AI research, but on the web of wisdom, explainable AI is needed for answering the why question, not only for solving problems. Based on this view, the sum of digital humanities and semantic web can perhaps be said as the web of wisdom. But how can we create a web of wisdom? Here are some lessons learned in Finland. Leonardo da Vinci has said, learn how to see, realize that everything connects to everything else. This wisdom is very true regarding cultural heritage data. However, cultural content linkedness gives us two major problems to tackle. The first key problem is that cultural heritage contents are richly interlinked, not only on a national scale, but across the borders of European countries and beyond. We all share common history and cultural background. For example, a book or epic may be the source of inspiration for a symphony, a painting, and is related to biographies of people, cultural sites, objects in museums, and so on. The cultural content includes texts, speech, images, 2D and 3D models, movies and animations represented in compatible formats using different national data models and using different national languages. The second key problem is that cultural heritage content creation is distributed in different kinds of organizations. When independent parties create content independently from each other, the result is an avalanche of data silos that do not speak with each other. To address these challenges, an open, reusable, and free semantic web infrastructure based on fair data is needed. The infrastructure for the semantic web is based on domain-agnostic Aristotelian logic that is not restricted by any natural language or application domain. This infra has been developed by the World Wide Web Consortium as an integral part of the general World Wide Web infrastructure. The domain-agnostic semantic web infra is nice for data linking, knowledge representation, and reasoning. However, it is not alone enough for applications. It needs to be extended by domain-specific national semantic web infrastructures because cultural contents and languages are country and application specific. We also need to combine recent results of sub-symbolic deep learning and large language models with symbolic semantic web technologies. The components of a national infrastructure are illustrated in this slide. For building application, shared ontologies, that is, Knowledge organization systems served by centralized ontology services are needed, as well as linked data services serving datasets and data models for research and for reuse. Applications are part of the infra too, as well as tools needed for developing the infra and its applications. As the web is developing quickly, building and maintaining a human infrastructure for using the infra is needed too. In Finland, this work is being carried out at the moment as part of the Finclaria Daria Fi research infrastructure initiative. Albert Einstein has said, "Intellectuals solve problems, but geniuses prevent them." This wisdom applies well to infrastructure building. Using a shared, standardized infrastructure when cataloging data in memory organization would make it much more cost efficient to break data silos later and to develop applications. How to build a national linked open data infrastructure. Experiences in Finland. The first international breakthrough in our research group was the system Museum Finland, Finnish Museums on the Semantic Web, published by the National Museum in 2004. It's the ancestor of the current Sampo systems and was awarded, among others, the Semantic Web Challenge Prize of the Semantic Web Research Community in Japan and the Prime Minister's Innovation Prize in Finland. Museum Finland is arguably the first museum publication system in the world based on the semantic web technologies and ontologies. The development of Museum Finland was challenging because the ontologies and tools needed for the project were not available. This gave rise to the vision that the development of the Finnish semantic web requires reusable, gradually evolving information infrastructure containing cultural data, which complements the W3C's generic technical infrastructure. Data must be made to flow seamlessly from one application to another, so that it is discoverable, accessible, interoperable, and reusable. At that time, the current FAIR principles were not known, but that was exactly what was at stake. With the help of some 50 partners and funders, a 3-year-long series of Finonto projects were launched. This work continues today at Aalto and University of Helsinki as part of the national Finclaria Daria Fi research infrastructure project related to the corresponding pan-European research infrastructures Claring and Daria. The ambitious vision of the Finonto project was to bring about a paradigm shift in the description of cultural and other fields content in the age of AI. The central keyword thesauri used in Finland were converted into semantic web ontologies, which were interlinked into a cloud of linked ontologies called Koko, using the YSO top ontology developed from the National Library's YSA thesaurus. At the same time, the YSA was translated into English so that Finnish ontologies and data could be linked to international materials. In addition, we ontologized, among other things, key biological nomenclatures and taxonomies of the Finnish Museum for Natural History, such as birds of the world, mammals of the world, and the Finnish names of plants in the Kassu database. On the geoinformatics side, an ontology was created from the National Land Survey of Finland's 800,000 place name register, which was later combined in NameSampo with the massive 2 million place name register of the Finnish Language Center for Toponomastic Research. An important part of our ontology work was the health ontologies, which were developed for our Health Finland system in cooperation with the Finnish National Institute for Health and Welfare and the Duodecim Doctors Organization. Health Finland prototype was later deployed by the Finnish Institute for Health and Welfare. Thesauri were transformed into lightweight RDF schema ontologies in order to facilitate reasoning, such as property inheritance along class hierarchies. Semantically vague terms with multiple meanings were split into several concepts that were repositioned into subclass of hierarchies. Broader than and narrower than relations were disambiguated into subclass of and part of relations, and fragmentary class hierarchies were completed into full subclass hierarchies. Even these small changes required several years of work. This image illustrates a part of the Ysä thesaurus on the left about keywords related to universities. On the right, the corresponding ontology is depicted with quite a different structure. For publishing and using ontologies, both by humans and machine via APIs, a special ontology server onki.fi was developed and published in 2008. The FinOnto community, for example museums, began to connect their cataloging systems to it. In 6 years, the point of no return was reached, and the Onki server could no longer be unplugged. In 2014, Onki was deployed by the National Library into the current finto.fi service, with funding from the Ministry of Finance and Ministry of Culture and Education. Today, tens of millions of API queries are made to its interfaces annually. The National Library has after this developed a software that's under Finto. Further, in the tools Cosmos, that is used today internationally by, for example, UNESCO and FAO of the United Nations. Research work at Aalto and the University of Helsinki continued after Finto as a new Link Data Finland project. The focus moved from ontologies to linked data and from Onki to the development of the Link Data Finland service. New application areas were added on the agenda. A key result of this work is the Link Data Finland platform ldf.fi, published in 2014. It's a bit like onki.fi ontology server, but for publishing linked open datasets. To encourage data publishers publish their data in a maximally reusable way, we extended Tim Berners-Lee's famous 5-star model, a ranking system analogous to one used in hotels. You get the 6th star if you publish not only your data, but also its data schema. 7th star is given if you provide a proof that your data conforms to the schema. 8th star is given if you can show that your data is truthful, that is, really corresponds to the factual real world. For example, the data from the Flat Earth Society could yield up to 7 stars if it's formally good, but will not get the 8th star. Each dataset on the platform gets a homepage of its own, generated automatically from its metadata. It's associated with a variety of tools such as a documentation generator, and a Sparkle endpoint is opened. This screenshot depicts the homepage of Parliament Sampo data that includes a knowledge graph of over 1 million speeches of the Parliament of Finland and another knowledge graph of the 3,000 parliamentarians who have spoken in the Parliament since 1907. The in-use portal Parliament Sampo, Parliament of Finland on the Semantic web is based on the Sparkle endpoint on the ldf.fi platform. How to use the infrastructure for applications, Sampo model and Sampo series of systems. Sampo systems are based on the so-called Sampo model, illustrated in this image, which has evolved over the years. It's based on a collaborative shared ontology infrastructure-based data service on the left in the image, which is used via the Sparkle interface in the application layer on the right. The data can be used through applications, such as by Sampo portals, or directly in digital humanities research by scripting and tools. The Sampo model is based on 6 principles, 3 for creating linked open data services and 3 for creating semantic portal user interfaces. Support collaborative data creation and publishing, use a shared open ontology infrastructure, make clear distinction between the linked open data service and the user interface, provide multiple perspectives to the same data, standardize portal usage by a simple filter analyze 2-step model, support data analysis and knowledge discovery in addition to data exploration. Since 2004, we have published over 20 linked open data services and semantic portals on the web based on the Sampo model. Culture Sampo publishes museum collections enriched by over 20 other types of data, including the narrative of the national epic Kalevala. Booksampo, with its 1.6 million annual users, is a joint work with the Public Libraries of Finland with a focus on Finnish fiction literature. Biography Sampo is based on the biographies of the National Biography by Finnish Literature Society. Name Sampo contains some 2 million place names in Finland for toponomastic research. War Sampo is based on data from the National Archives, Defense Forces and others. It's a popular web service visited by some 1.2 million distinct users. Letter Sampo is joint work with Oxford University, Huygens Institute of the Netherlands, and Berlin Brandenburg Academy of Sciences on epistolary data research. Sampo publishes data from the Schoenberg Institute in Pennsylvania, Bodleian Library in Oxford, and IRHD Institute in Paris. It's about medieval manuscripts. Parliament Sampo publishes all million speeches of the Parliament of Finland, and Law Sampo, Finnish legislation provided by the Ministry of Justice. Opera Sampo is joint work with the Sibelius Academy. We have learned that linked data technology works like a Swiss knife to different kind of data sets. The Sampo model is domain agnostic and can be applied in different applications. It is also possible to add a domain-specific ontology and data layer to the model and domain-specific user interface components, and in this way create domain-specific Sampo framework. Applying a domain-specific framework to a new similar application is then easier. For example, after creating the letter sample system for the EMLO database of the University of Oxford, it could be adapted and reused in other similar letter sample systems with different data. For user interfaces, we are using a tool called Sampo UI. Based on Sampo model, Sampo UI introduces a standard interface model and logic for using knowledge graphs, based on their key concepts: classes, instances, and properties. The model is easy to learn by end users and easy to use by developers. Sampo UI can be plugged in on top of virtually any Sparkle endpoint by adapting Sparkle queries to match the underlying data model and by modifying ready-to-use user interface components declaratively using JSON files. The landing page of the Sampo portal contains a series of windows that allow one to search, browse, and analyze the underlying knowledge graph from different perspectives, based on the classes of the knowledge graph. A perspective for a class contains faceted search engine whose facets are based on the properties of the class. By making selections on the facets, corresponding subset of individuals of the class are retrieved as the search result, and hit counts on the facet categories are updated to guide search. The result set can then be analyzed on different tabs, for example, on a map or timeline, or using graphs. At any point, an individual can be chosen for a closer look at its instance page that provides comprehensive linked data about the individual. Here it is possible to analyze and visualize data about the individual by using separate tabs too. Based on the same interface model, Sampo portals look the same and share similar functionalities. We have been happy with it and have not modified it much, even if this is also possible. In recent years, Sampo UI has been used by many foreign universities. For example, researchers of the University of Latvia presented the Nobel Prize Sampo at the Vienna Semantic Conference in 2025. It is based on the Sparkle endpoint service of the Nobel Foundation in Sweden. The Geneva Graduate Institute in Switzerland has implemented Sampo based on Parliament Sampo for the minutes of the General Assembly of the League of Nations. Let us have a look at the Sampo system. Letter Sampo historical letters on the Semantic web.
This video introduces the Letter Sampo project at the Aalto University and Helsinki Center for Digital Humanities Helsinki. We are developing a framework and a demonstrator for publishing and analyzing historical epistolary data in digital humanities based on semantic web technologies. This new project in Finland was inspired by our earlier collaborations with the Pan-European EU Cost Action Reassembling the Republic of Letters and the University of Oxford. related to historical letters sent from the 16th to 19th century in Europe and beyond. Letters are always sent from a place to another and are therefore scattered in different archives in different countries, written in different languages, harmonizing the metadata from separate data silos and aggregating the data into a semantically interoperable global service for digital humanities analyses makes a nice use case for the SAMPO model and SAMPO UI framework, developed at the Semantic Computing Research Group. The SAMPO model includes a collaborative business model for collaborative data publishing in a shared linked data service, the idea of accessing the data from multiple perspectives, the idea of integrating the service seamlessly with data analytic tools for research, and finally, a model for addressing research questions in 2 steps, where faceted search is first used for filtering out data of interest, and data analysis and visualizations are then applied to it. We next illustrate this idea by showing examples on analyzing letter data by using the Letter SAMPO demonstrator. This is the main entry page for the Letter SAMPO user interface. The application consists of 3 perspectives to the underlying data: the actors, the letters, and the places. The underlying dataset in this example contains information about a total of 34,000 actors. By actor we mean an individual person or group of people like universities or religious organizations. In the faceted search we can filter or search specific actors by their name, gender, or times of birth or death, or groups of actors for prosopographical research. For example, we can search for the mathematician Gottfried Wilhelm Leibniz. On the result page we will see him among the other matches. The result table shows his years of birth and death, and the amount of the letters involved, based on the underlying metadata. On the person landing page we will have even more information about him and his correspondences. In addition to showing his basic biographical information, the page contains fields for his alternative names and vocations. There is a list of all the other actors with whom he has been in contact. It should be emphasized that any visualization or data analysis in a system like Letter SAMPO is an analysis of the underlying dataset, not of the real world. Any conclusions drawn from the analysis need source criticism and understanding the limitations of the data. For example, in this example there are 149 letters of Leibniz and the data misses lots of letters. Leibniz was a very active writer with some 15,000 letters and 1,100 correspondence. So in this case only 1% of those are available in the demonstrational dataset. In spite of this, analyzing an incomplete letter collection by distant reading can give novel insights to the researcher and collection manager, and suggest topics of interest for further close reading. The first person on the list is Christian Huygens, with whom he has sent 70 letters, as far as the data can tell us in this case. There are also detailed lists of all letters sent or received by him. The last result on this page shows a list of places he has been active and based on data about sending or receiving letters. The next tab, Network of Letters, shows a visualization of actors' egocentric network. The link width between 2 actors indicates the amount of mutual correspondence. The wider the link, the more letters has been sent between the 2 actors. We can for instance spot that Leibniz sent 39 letters to Christian Huygens, while Henry Oldenburg sent more than 200 letters to Huygens. Again, this analysis is based on data about only a fraction of Leibniz known letters. The next tab illustrates the number of letters on a timeline, where we can observe that the data is based on letters from 2 periods, the first one in the 1670s, and the second in the 1690s. This could indicate the collection manager that letters in between may be missing. The letter perspective page has a similar faceted search application as the actor page. Here we can browse and filter the data of 162,000 letters by their sender, receiver, date, language, subject, or data source. The second tab on the letter page visualizes the letter routes on a map application. Currently we are viewing the routes of letters sent from Paris. The third tab on the letter page demonstrates the amount of correspondences on a timeline. From this curve can be seen that the data is distributed from 16th to 19th century, with the majority of letters in the 17th century. In addition to the ready-to-use data views in Letter SAMPO, The underlying Sparkle endpoint can be used easily for further data analysis using, for example, Python scripting in Google Columns. This data table shows the most active mathematicians in the data set, filtered out from the data. The left column shows the actors ranked by the number of letters sent. In the middle column, ranking is based by the number of received letters, and on the right by the total amount of letters. The blue text color indicates that the actor has written more letters than what he has received. This is a visualization of the top writers between the years 1620 and 1770, and the ranking of the author is depicted on the y-axis, so that the highest ranking actor appears on the top of the diagram. Based on the underlying collection data, in the 1620s and 1630s Marin Mersenne was at the highest rank. Christian Huygens was among the top writers during the years 1650 to 1690s. Isaac Newton has been an active writer in the late 17th and early 18th century. And finally we have Leonard Euler, who's been the top writer during 4 decades from 1730s to 1760s. Thank you all for watching this video. More information about the Letter Sampo project is available at the web page of the Semantic Computing Research Group.
The result of our work on Sampo systems has been a linked data cloud of Sampo knowledge graphs. They cover a wide range of cultural heritage domains such as artifacts, art, folklore, letters, military history, music performances, literature, biographies, academic traditions, archaeological collections, parliamentary speeches, place names, and legislation. How could this cloud be utilized as a whole? To address this question of utilizing the Sampo cloud, we started to develop a kind of meta Sampo called Sampo, connecting everything to everything else, according to the quote of Leonardo da Vinci. Sampo applies the Sampo model to the Sampo cloud of knowledge graphs and other data services. The idea is to develop a new data service that links Sampo entities, such as people and places, to each other and enriches the materials with links to external data services. On top of the LOD service, the semantic portal Sampo was created. Sampo aims at 4 practical use cases. Firstly, Sampo can be used to enrich data when creating samples. Secondly, Sampo search and other functionalities can now be extended globally across different samples. Thirdly, the system allows for quality checking of the interlinked datasets by comparing data available from different primary sources. Fourthly, Sampo offers the opportunity to discover new interesting connections between entities in the data and explanations for these in natural language. Sampo's linking service resembles VIAF, the Virtual International Authority File, an international entity linking service between national library collections around the world. The idea of entity linking has also been applied in the same as links that connect entities in the knowledge graphs of the Linked Open Data Cloud and in the Linked Open Vocabularies project. Sampo data is available at the Linked Data Finland platform, where it can be accessed and utilized by using a Sparkle endpoint. The data can be downloaded from Zenodo. We have used Sampo in enriching the data of the Letter Sampo Finland system that publishes data about 1.3 million letters from the 19th century Grand Duchy of Finland. The idea of global search, browsing and data analysis across samples based on globally enriched contents is demonstrated by the Sampo portal. Its landing page contains application perspectives for people, organizations, places, and explained relations between entities, and a listing of primary data sources. There are also shortcut links to example searches and data analysis. In this screenshot, the user has opened the people perspective. From the facets on the left, she has selected gender is female, and the result 20,000 women out of 98,000 people is shown on the table tab on the right. The result includes, for example, Helen Scherfbeck, the painter. By clicking on Helene Scherbeck, her aggregated enriched metadata and links can be studied. The result set can be visualized and studied in different ways on the tab. Here the lifelines of women from their place of birth to place of death are shown as color-coded interactive arcs. By comparing data about entities in different datasets, Sampo can also be used for checking the quality of the primary sources. It's possible to find obvious errors. For example, according to Academy Sampo, Mr. Carl Henrik von Norring lived between 1793 and 1863, but the National Bibliography Database Kanto of the National Library gives 1973 for the year of birth, which is clearly a typo. We have also found lots of contradictions, such as two close birth years of Mr. Gustav Walfrid Vasenius. Also possible duplicates in the data can be found. It is then up to the data owners to check whether their own data or that of their fellow organization is wrong. For example, this screenshot of the instance page of Bishop Mikael Agricola, known as the father of Finnish language, shows in red disagreements between datasets regarding the times of birth and death as well as the place of death. The data sources are indicated as provenience data links. By using the facet inconsistency type, it is possible to search inconsistencies systematically. For example, we found 42 issues with the gender of the people. By using the data source facet, it is possible to find by 2 clicks all potential inconsistencies in a particular dataset for corrections in the primary data. For example, the public libraries of Finland used this possibility to correct their data in BookSampo. In the first version of Sampo, thousands of inconsistency issues were found as listed in this graph visualizing the distribution in the inconsistency type facet of the people perspective. In addition to people, also inconsistencies of places based on their coordinates can be analyzed in Sampo. The idea here is to compute a kind of average sampled coordinate point for the location using the aligned places, and then mark those who differ from it more than a criterion as inconsistent. The image shows different coordinates used for Canada in different datasets. The final use case of Sampo is knowledge discovery of new or even serendipitous connections between entities with natural language explanations. 2 methods have been tested here. Relational search by exploring link chains between entities and using generative AI and large language models for reasoning relations. Our approach was to design a data model and the relation class of explained relations and then generate instances of relations in different ways into a knowledge graph. The relation instances can then be searched for and studied as usual in Sampo UI-based portals. The first version of Sampo contains over 190,000 relations generated in this way as listed in this slide. Recently, a subject of intensive research has been the combination of large language models and knowledge graphs into neurosymbolic AI. Here language models are used to solve the limitations of knowledge graphs and, on the other hand, knowledge graphs are used as a remedy for the problems of language models. In Sampo, large language models have been used to automatically build knowledge graphs and in knowledge discovery of new relations with explanations. The underlying knowledge graph has been used to create prompts for large language models using the retrieval augmented generation methodology. This screenshot illustrates how faceted search can be used for knowledge discovery between people and places. On the left, the facets for persons, places, relation types, and data sources can be seen. 14 relations of 4 different types with explanations were found on the right for the painter Elien Danielsson Kambodži, 7 from Art Sampo and 7 from Biography Sampo. The relations include the career or studies of Elien Danielsson Kambodži are related to an event in Paris. She studied at the Académie Colarus in Paris 1883 to 1885, and Danielson Campozzi has created the artwork on Lake Massa Chioccioli, which depicts a location in Italy. In this screenshot, people-place relations are used to enrich a person's instance page of the Map tab. Here, the 145 places related to Marshall Mannerheim in different ways are shown. By clicking on the marker in Denmark, related relations are found, such as getting the Order of Elephant decoration, the highest honorary medal of Denmark. Summary. This timeline summarizes our work on building and applying the national semantic web infrastructure in Finland in relation to major international developments and phases, where ontologies, the silver bullet of the semantic web, were first in focus. After that, ideas of linked data publishing took off, and during the last 10 years, ontologies and linked data have been studied together as knowledge graphs in various domain-specific application settings. We are now entering the time of AI and neurosymbolic intelligent systems. The work in Finland has followed exactly the same pattern with major projects such as FinOnto for ontologies, Linked Data Finland for linked open data, and various sample projects on knowledge graphs. Also, first steps towards knowledge discovery and AI have been taken. All work has been based on standards and best practices of W3C and others illustrated at the bottom. During these years, we have learned that it makes sense to develop shared LOD infra step by step together with all stakeholders involved. For cost-efficient work, it is important to reuse the shared LOD infra for applications. LOD technology is very resilient for different domains and languages and can be reused in different kinds of applications. And finally, using LLMs with knowledge graphs opens a promising way to neurosymbolic AI, where the complementary strengths of subsymbolic and symbolic AI are harnessed. In Douglas Adams' novel Hitchhiker's Guide to the Galaxy, artificial intelligence was asked about the purpose of life, the universe, and everything. The result of the calculation for 7.5 million years was 42. The answer may be correct, but it would be nice to know why 42. Especially in digital humanities, AI needs not only problem-solving skills, but also the wisdom to answer the why questions. This is being studied in the research area for explainable AI. With such AI, we can take the next steps forward towards the web of wisdom. More information, publications, and links to different samples and infrastructure services can be found on the home pages of the Semantic Computing Research Group.